Welcome to Math with ACE. We are focusing on statistics today. We are performing a hypothesis test all the way through. We're going to be setting up our hypotheses, checking conditions, calculating the test statistic, and then determining whether there is evidence in our conclusion and doing that in context. So let's get into this problem and highlight the important things before we set up our null and alternative hypothesis. June believes that 50% of first-time brides in the United States are younger than their grooms. She performs a hypothesis test to determine if the percentage is the same or different from 50%. June randomly samples 100 first-time brides. 53 reply that they are younger than their grooms. Perform a hypothesis test at the 1% level of significance to determine if there's evidence to support June's claim. So for this problem, we have a lot of information in terms of younger versus different. Which one is our claim? First of all, we are told 50% is what she's comparing. So June is performing a hypothesis test to determine if the percentage is dealing with the categorical data of yes or no being younger or not. This is a proportion problem. And we're talking about 50%. But her hypothesis test is it is the same or different. That is a not equal to problem. I understand that the younger is in there, but that we're not talking about the average age. This is not a problem about average age. It's the percentage that either meet that condition or not. And so P is the true proportion of first-time brides in the US that are younger than their grooms. We are going to test this at the alpha equals 0.01 level of significance because that's what we've been given in the problem. Now we want to check our conditions. First, random. We did highlight that the sample June did was randomly sampled, so we're going to go ahead and state that the problem was randomly sampled. June randomly sampled 100 first-time brides. That means that N is 100. So in order to determine if that's less than 10% of the population, we can take that sample and multiply it by 10 to determine if our population is larger than that. These are first-time brides in the United States. Is there at least 1,000 first-time brides in the US? Yes, there are. For normal large counts, we have to remember that this is hypothesis testing, and we're looking at what we would expect to happen. I'm going to move this up a little bit. We need to be comparing successes and failures that are expected, which means we are using the hypothesized value when comparing to 10. Our sample size of 100 times our hypothesized value of 0.5 is 50. So successes of 50 are at least 10. 100 times 1 minus 0.5 also gives us 50. So both successes and failures are at least 10. So now we can proceed. we are going to calculate the test statistic. In our do, we want to include the point estimate or your sample proportion. You want to include your sample size. You need to include your z-value and your p-value, which is based on your z-value. So p-hat, the sample proportion, there were 53 out of 100 that said that they were, in fact, younger than, or first-time brides that were younger than their grooms. The sample size was 100, and our z-value is found by taking your sample value minus your hypothesized value and dividing that by the hypothesized value times 1 minus the hypothesized value over n. Using the values for this problem, 53 divided by 100 is 0.53. So we're going to take 0.53 minus 0.5, and we're going to divide that by the square root of 0.5 times 1 minus 0.5 divided by 100. So 0.03 divided by 0.05 gives us 0.6. When you take the square root of 0.5 times 1 minus 0.5 divided by 100, you do get 0.05. So that quotient is 0.6, which is pretty close to the average, honestly. So the p-value, I don't expect to be, I expect it to be larger. So what I'm going to do is I'm just going to go into normal distributions, and I'm going to calculate the area where the mean is 0 and the standard deviation is 1. I'm going to plot that distribution, okay? And we're talking about a z-score of 0.6, but I need to know my direction. My direction is not equal to, but it's a positive. So let's say it's to the right of 0.6. That area is 0.2743. I'm going to write that down. But if I was to say to the between or outside a region, what are my 0.6, negative 0.6? If I was to get negative 0.6 and positive 0.6, I then have 0.5485. I shouldn't be putting percent signs, it's a decimal. You might be thinking, well, why are you doing that? Why are you taking a negative? Our z-score was not negative. When you are performing a hypothesis test that is two-tailed, if you are negative, you're going to do area to the left then, and then double it. If you're positive, you do area to the right of, and then double it. The actual probability of obtaining the data that we did, or data more extreme, because you can reject high or low, is double what a one-sided would be. So the p-value for this problem is actually 0.5485. This means 55% of the time, we would get a sample proportion of 0.53 if the population proportion is really assumed to be 0.5. So what this means is that happens a lot. So since our p-value of 0.5485 is not less than our alpha equals 0.01. Level of significance, not less, not reject, no evidence. Okay. There is insufficient evidence to support the claim. What's the claim? We want to give it in context. And it is that It's different. So first-time brides in the US are younger than their groom. That the true population proportion of first-time brides in the US is different than 50%. All right. Thanks for sticking around, y'all.